Welcome to today's problem walkthrough. In this session, we'll tackle an interesting coding challenge titled Day of the Year. This problem will test your understanding of date calculations and iterative logic. Let's dive right in. In this problem, we are tasked with determining the day number of the year for a given date. The input date is provided as a string in the format YYYYMMDD, which represents a Gregorian calendar date. The day number of the year is simply the count of days that have passed since January 1st of that year, including the given day. For instance, if the input date is January 9th, 2019, it means that January 9th is the 9th day of the year. Therefore, the output for this input would be 9. To further clarify, let's look at the example of January 9th, 2019. This date corresponds to the 9th day of the year 2019 because it includes all 9 days from January 1st to January 9th. Now consider another example, February 10th, 2019. In this case, the output is 41. Here's why: January has 31 days, and when we add the 10 days from February, we get a total of 31 plus 10, which equals 41. This means February 10th is the 41st day of the year 2019. Now let's examine the example of March 1st, 2003. This date corresponds to the 60th day of the year 2003. To calculate this, we add up the days in January, which are 31, the days in February, which are 28 because 2003 is not a leap year, and finally the 1 day from March. This gives us a total of 31 plus 28 plus 1, resulting in 60. Additionally, we must consider constraints for this problem. The input date will always be valid, adhering to the Gregorian calendar. The input format is fixed at YYYYMMDD, and the year will always be between 1900 and 2100. There are a few edge cases to keep in mind. If the year is a leap year, February will have 29 days instead of 28. Leap years occur if the year is divisible by 4, but not divisible by 100, unless it is also divisible by 400. For example, the year 2000 is a leap year, but 1900 is not. Additionally, dates at the very start or end of the year, like January 1st, 1900 or December 31st, 2100, should be handled correctly. These are the types of considerations required to ensure the solution is robust and accurate for all valid inputs. To determine the day of the year for a given date, there are multiple approaches we can consider. The first is the brute force approach, where we iteratively count the days month by month. The intuition here is straightforward: we add up the days of all months from January to the month just before the given month. Then, we add the day component of the date itself. This involves parsing the date string to extract the year, month, and day, and using a predefined list of days in each month. When dealing with February, we check if the year is a leap year. This is determined by whether the year is divisible by 4 but not by 100, unless it's also divisible by 400. If it is a leap year, February is adjusted to have 29 days instead of 28. Finally, we sum up all the days and return the result. While this approach is simple to implement and has a time complexity of O(m), where m is the number of months, it does involve iterating through the months, which introduces a slight inefficiency. Now, let's look at the optimized approach, which avoids iterating through all the months by leveraging pre-computed data. Instead of summing days month by month, we use an array of cumulative days for non-leap years. This array allows us to directly calculate the total days up to the given month. The steps are as follows: first, we parse the input date to extract the year, month, and day. Then, we use a cumulative days array like 0, 31, 59, 90 to get the total days up to the previous month. If the given year is a leap year and the month is after February, we add one extra day to account for February's additional day. Lastly, we add the day component of the date to the cumulative total. This approach has a time complexity of O(1), because all operations are constant, and it avoids iterating through months entirely. While it does require storing the cumulative days array, the memory overhead is minimal. This method is faster and more efficient, making it an excellent choice for scenarios where performance matters. Given the options, we chose the optimized approach using cumulative days for non-leap years as our strategy. This method strikes a balance between simplicity and efficiency. It avoids the repetitive iterations of the brute force approach and eliminates the dependency on external libraries seen in the library-based solution. The memory cost of the cumulative days array is negligible, making this approach ideal. One key insight is that leap year adjustments only apply to February and later months, which simplifies the logic further. By pre-computing cumulative days, we can use direct indexing to achieve constant time complexity, making the solution both elegant and performant. When comparing approaches, the brute force method is straightforward but less efficient, while the library-based approach is easy to implement but lacks flexibility in customized scenarios. Ultimately, the optimized approach is the best choice for competitive programming and interviews due to its speed, minimal code, and independence from external libraries. To solve the problem of determining the day of the year for a given date, we can break the algorithm into clear steps. First, we need to understand the core goal: calculate the day number by summing the days of all previous months and adding the current day's value. This requires us to account for the varying number of days in each month and also handle leap years, as they affect February's day count. The input consists of 3 integers, month, day, and year, and the output is a single integer representing the day of the year. We'll also need to implement leap year logic, as this is critical for accurately calculating the total number of days in the year. Now, let's dive into the specifics of leap year logic. A year qualifies as a leap year if it is divisible by 4 but not divisible by 100, unless it is also divisible by 400. This means 2000 is a leap year, but 1900 is not. After determining whether a year is a leap year, we define the number of days in each month. For a non-leap year, we use a list where February has 28 days. If the year is determined to be a leap year, we update February's day count to 29. With this setup, we can now sum the days of the months preceding the given month. Using slicing, we sum the days from the start of the list up to the given month's index -1. Finally, we add the day value from the input to this total to compute the day of the year, which we return as the result. There are a few key insights that make this algorithm both efficient and reliable. First, the leap year calculation is pivotal because it directly impacts February's days. For example, February 29th in a leap year like 2020 must be accounted for accurately. Second, using a zero-based index for the days in the month list simplifies our logic. By slicing up to month 1, we ensure the summation includes only the months prior to the given month. The iterative summation of days from the months is straightforward, avoiding unnecessary complexity. It's also important to consider edge cases, such as dates and leap years, the first day of the year like January 1st, and the last day like December 31st. Additionally, we should validate inputs to handle invalid dates, such as a month greater than 12 or a day exceeding the maximum for a given month. The algorithm relies on 2 simple data structures. First, a list is used to store the number of days in each month. This allows constant time access to the days for any specific month. Second, an integer variable accumulates the total number of days by summing the days of previous months and adding the current day. With these data structures in place, the final algorithm is concise and efficient. The function starts by defining the days in each month for a standard year. If the year is a leap year, February's value in the list is updated to 29. Next, the algorithm sums the days of all months leading up to the input month using slicing and the sum function. Lastly, it adds the day value to this total, and the result is returned. After adding the current day to the total sum of the previous months, the function returns the computed day of the year. Let's walk through an example to solidify our understanding. Suppose the input is month 3, day 15, and the year 2023. First, we check if 2023 is a leap year. Since it is not divisible by 4, it is not a leap year, and February remains at 28 days. The list of days for all months is thus 31, 28, 31, 30, 31, 30, 31, 31, 30, 31, 30, 31. Next, we sum the days in January and February, which gives 31 plus 28, totaling 59. Finally, we add 15 days for March, resulting in a total of 74. This means that March 15, 2023, is the 74th day of the year. The output of the example is 74, confirming that March 15 is the 74th day of the year. Let's analyze the complexity of the algorithm. In terms of time complexity, the algorithm involves iterating through the list of months up to the given month. In the worst case, when the input month is December, this requires at most 12 iterations, which simplifies to 1 constant time since the maximum number of iterations is fixed. For space complexity, the algorithm uses only a fixed size list for the days in each month and a few integer variables for calculations. This results in 1 space usage. Given the simplicity of the input and the constraints of the problem, the algorithm is already optimized and does not require further enhancements. Pre-computing cumulative day counts is unnecessary due to the limited scope of this calculation. This makes the algorithm both efficient and well-suited for the problem. Its constant time and space complexity ensure it handles any valid input date effectively within the bounds of the problem constraints. This Python implementation calculates the day of the year for a given date, accounting for leap years. First, we define the day of year function within the solution class. The function takes a string date in the format yyyimmdd. To start, we define a list days_in_month, which contains the number of days in each month for a non-leap year. Next, we parse the input date string into integers for year, month, and day using Python's map and split functions. This allows us to easily work with the individual components of the date. To handle leap years, we check if the year satisfies the leap year conditions. A year is a leap year if it is divisible by 4 and not divisible by 100, unless it is also divisible by 400. If the year is a leap year, we update February's days in the days_in_month list to 29. Finally, we calculate the day of the year by summing the days of all months prior to the given month, using slicing in the sum function, and adding the day of the current month. The result is returned as the day of the year. This implementation is efficient and handles all edge cases, including leap years. Here, we start by defining the day of year method, which takes a date in the format yyyimmdd as its input. First, we initialize an array days in month to represent the number of days in each month for a typical non-leap year. Next, we parse the input date by splitting the string using the hyphen as a delimiter. This gives us the year, month, and day as integers. With these components extracted, we determine whether the given year is a leap year. A year is considered a leap year if it is divisible by 4 but not by 100, unless it is also divisible by 400. If the year happens to be a leap year, we adjust February's days in the days in month array from 28 to 29. Now, to calculate the day of the year, we iterate through the months prior to the given month, summing the number of days in each. Finally, we add the given day of the month to this sum to account for the current month. The final step is straightforward. Once we have calculated the total number of days by summing the days from previous months and the current day, we simply return this value as the result. This represents the day of the year for the given date. The method is efficient and handles both leap years and non-leap years correctly by dynamically adjusting February's days when necessary. With this, our implementation is complete, providing an accurate way to determine the day of the year for any valid date input. To solve this problem, let's start by parsing the input date string. For the example input March 1, 2023, the string is split into 3 components: the year, which is 2023, the month, which is 3, and the day, which is 1. Now, we need to account for the number of days in each month for a non-leap year. This is represented by the list days_in_month, where January has 31 days, February has 28, March has 31, and so on. Since 2023 is not a leap year, the number of days in February remains 28. We confirm this by checking the leap year condition. A year is a leap year if it is divisible by 4 but not by 100, or if it is divisible by 400. For 2023, this condition is false, so we set is_leap to false, and the days_in_month list remains unchanged. Finally, we calculate the day of the year by summing the days of all months before March, which gives us 59 days, and then adding the current day, resulting in a total of 60. Therefore, March 1, 2023, is the 60th day of the year. Now let's look at a second example with the input February 29, 2024. First, we parse the input into year equals 2024, month equals 2, and day equals 29. As with the previous example, we initialize the days_in_month list for a non-leap year, where February has 28 days. However, since 2024 does satisfy the leap year condition, being divisible by 4 and not 100, or divisible by 400, it is a leap year. Thus, we update February's days from 28 to 29 in the days_n_month list. This adjustment ensures that we accurately account for the extra day in February when calculating the day of the year for leap years. With February now correctly adjusted to 29 days, we calculate the day of the year for February 29, 2024. First, we sum the days of all months prior to February. Since January has 31 days, this sum is 31. Adding February's 29 days to this total gives us 60. Therefore, February 29, 2024, is the 60th day of the year. Next, let's consider a third example, December 31, 2000. Here, the input is split into year equals 2000, month equals 12, and day equals 31. Once again, we start with the days_n_month list for a non-leap year, where February has 28 days. In this case, we need to determine if the year 2000 is a leap year. Since it satisfies the leap year condition, being divisible by 400, it is indeed a leap year. As a result, February's days are updated to 29 in the days_n_month list. To calculate the day of the year for December 31st, we sum the days of all months prior to December. This total is 335 days. Adding December's 31 days gives us a final result of 366. December 31st, 2000, is the 366th day of the year because 2000 is a leap year. To summarize, the solution involves parsing the input date, initializing the days for each month, determining if the year is a leap year and adjusting February accordingly, summing the days of months prior to the given month, and adding the current day to find the total. This process allows us to compute the day of the year for any valid date input. To analyze the time complexity of our solution for the day of the year problem, we note that the entire process runs in constant time, or O1. First, the input date string, which is always in the fixed format YYYIMMDD, is split into three components: year, month, and day. Since the string length and the operations are bounded, this step takes constant time. Next, we calculate whether the year is a leap year using a simple Boolean expression. This involves a few arithmetic and logical operations, each of which runs in O1. If the year is determined to be a leap year, we adjust the number of days in February by updating a single value in the days_n_month array. Modifying an array element is a constant time operation as well. Finally, we compute the sum of the days for all months preceding the given month. Since the array days_n_month is fixed at 12 elements, summing a subset of these elements is bounded and takes O1 time. These steps collectively show that the time complexity is indeed O1. Adding the current day of the month to the previously computed sum is a straightforward arithmetic operation, which also takes constant time. Altogether, the solution does not include any loops or operations that depend on the size of the input, so the overall time complexity remains O1. Now, looking at space complexity, the memory usage of the solution is also O1. The input date string has a fixed size of 10 characters, and the days_n_month array, which stores the number of days in each month, occupies a constant amount of space with 12 integers. Additionally, temporary variables such as year, month, day, and is_leap are scalar values, meaning they use constant space as well. This ensures that the memory usage is fixed regardless of the input date. Since no additional data structures are introduced, and we avoid recursion or dynamic memory allocation, the total space complexity remains O1. By comparison, a naive approach might involve iterating through all the days from January 1st to the given date, incrementing a counter for each day. This would result in a time complexity of O(d), where d represents the number of days from the start of the year to the target date. However, this approach is inefficient because we already know the number of days in each month and can pre-compute them. By leveraging the days_n_month array and directly summing the required values, our solution avoids iteration and achieves O1 time complexity. Mathematically, this is justified because the operations performed, such as parsing and summation, are constant and do not scale with the input. Similarly, the use of a fixed-size array ensures that memory usage remains stable. Finally, let's analyze the best, average, and worst-case scenarios for this algorithm. Regardless of the specific date provided, the algorithm processes the input in exactly the same way. Whether the input represents a date early in the year, such as January 1st, or late in the year, like December 31st, the operations remain constant. This consistency ensures that the time and space complexity are O1 in all cases. The performance does not vary based on the values of the year, month, or day, making the algorithm extremely efficient and reliable for any valid input. One of the most common mistakes in this problem is forgetting to account for leap years. Leap years occur when the year is divisible by 4, but not by 100 unless it's also divisible by 400. This directly affects the number of days in February, so handling this correctly is essential to avoid errors. Another frequent issue is incorrect indexing when working with an array that stores the number of days in each month. For example, if your implementation assumes January starts at index 1 but your array starts at index 0, you might end up accessing the wrong month. Testing boundary cases like December 31st or January 1st can help catch these kinds of indexing or summation errors. Additionally, hard-coding the number of days for each month using multiple if-else or switch statements can lead to inefficiencies and mistakes. Instead, using a predefined array for the days in each month is cleaner and less error-prone. Finally, always validate your inputs. Dates like February 30th are invalid and should either raise an error or be handled appropriately in your implementation. Now, from an interview perspective, this problem is often used to assess your ability to recognize patterns in arrays, handle edge cases, and implement conditions like leap year checks. The way you structure and modularize your code is something interviewers pay close attention to, so aim for clarity and simplicity. While brute force solutions are acceptable for simpler versions of the problem, interviewers might push you to think about optimizations, such as pre-processing cumulative sums for handling multiple queries efficiently. Explaining your thought process clearly is just as important as getting the correct solution. Be sure to articulate how you validate inputs and manage leap years. In terms of time complexity, iterating through months is O1, since there are always 12 months in a year. For scenarios with multiple queries, pre-computing cumulative days can result in significant efficiency gains. Additionally, this problem is closely related to others like LeetCode 1360, which involves calculating the difference between two dates, or LeetCode 1185, where you find the day of the week for a given date. These related problems build on similar logic and can help reinforce your understanding of date manipulations. There are also alternative approaches that can make solving this problem more efficient or adaptable. One option is to use pre-computed cumulative sums. For instance, you can create an array where each element represents the total number of days up to the end of that month. In a non-leap year, this might look like 0, 31, 59, 90. By pre-processing this array, you reduce the runtime for each query to O1, since you can directly access the cumulative days. The trade-off here is the slight increase in memory usage for storing the array, but it's often worth it for the efficiency gains. Another approach involves deriving a direct formula to calculate the day of the year, though this is typically less intuitive and harder to generalize. It's best suited for specific constraints and scenarios. Finally, you might use built-in libraries like Python's datetime to handle date calculations. This method is fast and concise, but it's important to note that such libraries may not be allowed in competitive programming or interviews, where the goal is to demonstrate your algorithmic thinking. Each of these approaches has its strengths and trade-offs, so choose the one that best fits the problem requirements and constraints you're working with. Great job making it to the end. We've summarized the approach, discussed its complexity, and highlighted the key takeaways. Remember to practice similar problems to strengthen your understanding. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!